Right. Welcome, everyone. So we are delighted today to have Tengyu Ma from Princeton University. So Tengyu is a student of Sanjeev Arora, and he's going to tell us about non-convex optimization.
Okay. Thanks for having me here, and thanks for coming. So I changed my title and the content a little bit. So I'm still going to talk about matrix completion as promised, but in the last 10 or 15 minutes, I'll mention some recent work with Maurice Hart on linear residual networks, which I'm quite excited about. So the matrix completion one is joint work with Rongo and Jason Lee from Duke and USC, and the last one, the linear residual network one is with Maurice Hart. I'm Tengyu Ma from Princeton. So I'm going to talk about non-convex optimization. So just to put this talk into a little bit broader context. So let's start by comparing convex optimization with non-convex optimization for machine learning problem. So on the convex side, we have a beautiful theory about convex functions. We have fast algorithms for pretty much all of the situations, like smooth, non-smooth, strongly convex, non-strongly convex, a sum of convex functions. And these algorithms are fast in practice and in theory. So on the other side, non-convex optimization in the worst case is NP hard. So it sounds like we don't even have a comparison here, right? So on one side we have everything, and on the other side we have nothing. So, but sometimes you have to think about it and ask the question: what if you really want to optimize a non-convex function, right? So in terms of machine learning, this means that corresponds to what. If you want to optimize, you want to learn some complex models beyond, linear models. Like, if you want to do neural network with empirical risk minimization, or if you want to maximize log likelihood for, many generative models, like for example, mixture of Gaussians. So, the kind of the recipe that the convex world offers us is the idea of linearization. So linearization could mean probably two things. One is the kernel machine, right? So you lift your feature, your input into a higher dimension, and in the new space you learn a linear classifier. So that's one way to linearize your model, and the other one is that you can do convex relaxation, which linearize your variables. So you introduce the auxiliary variables, and to make it linear, and there's a generic way to do all these convex relaxations, like sum of squares relaxation these days. I love this posted method. Actually, I worked on some of the convex relaxation things. But however, it seems that we have to admit that these are not efficient enough, right? Often you can get, polynomial dependency on either number of examples or the dimension. But, these days, you have 1 million examples, and the number of parameters is something like probably 10 million. As long as you get something like n squared, d squared, if n is example number of examples, it's going to be a disaster. So it seems that they are not efficient enough. On the other side, there's a very simple way to do non-convex optimization in practice. You just do stochastic gradient descent. So these are, very scalable, very easy to implement. These days we have all this auto differentiation package, like, TensorFlow. I apologize, I still use TensorFlow in my talk. Maybe I should choose something from Microsoft. But anyway, so you don't even have to write down your compute your gradient by yourself. You just need to write down your model, and with another 2 lines of code, you take the gradient and do whatever optimizer you want. So, all right. So everything is perfect here except the Elex theory. So it works, and it works perfectly well. It is the main algorithmic technique behind all of these breakthroughs in NLP, in computer vision, like speech recognition. So, but we don't really know too much about the theory behind it. So the question that I'm asking in general here is that can we understand non-convex optimization better and improve it? So I mentioned that it is simply hard to optimize non-convex functions in the worst case. However, the hope here is that, for structured learning objective functions on real-life data, it's very likely that these problems are not NP hard. And we have a strong empirical evidence for that.
So one question. So is there a notion of like approximations for non-convex in the way we deal with NP hardness in combinatorial optimization?
I guess you can, but it's not clear whether those approximation guarantees can lead to anything for machine learning problem. Maybe sometimes it can, but but you have to argue about that. Like, it's not like the optimization is not the only goal, especially for machine learning, So, and also the way to phrase approximation also probably is different, right? Probably multiplicative approximation may not mean anything. You maybe need additive approximation, so on and so forth. Okay, so let me have a list of problems that can be solved by non-convex machine in machine learning. This is just a partial list. I try to sort these problems according to the difficulty of the analysis, and my criteria is my very biased opinion is my criteria is the lack of linear algebraic structures. Of course, also difficult analysis doesn't really mean everything. So, but let me just list it according to this criteria. So kind of the ultimate goal, probably in the short term, at least, is to understand how to train neural network or other variants like a recurrent network, long short-term memory. So, and these are problems that we don't know how to do in theory, but empirically we can do it very well. So, in terms of theory, what we could analyze and understand these problems. So, I guess for SVD and PCA, these are folklore, and the only way to do it is using non-convex methods. I guess this line of research really starts with the generalized linear model by the study by Kallai et al. And also Hazen et al. Has some other study about it. So, and also recently we know that if you do SDP, you can, for example, if you have a small number of constraints in your SDP and you know that the optimal solution is of low rank, so you can try to use the low rank parametrization and do gradient descent for the SDP. And we know that for generic SDP, this can be solved in polynomial time. And also there are works on linear deep neural networks and linear residual networks, which I'm going to touch on a little bit at the end of the talk. And for matrix completion, this is the main subject of this talk. And Gaussian mixture model. For linear recurrent network, this is the joint work with Maurice Hart and Ben Recht. So the kind of the difficulty is that you have to apply some linear transformation again and again. So you have a power of some matrix, which is not exactly within the scope of a linear algebra. So you have to do something special for it. And finally, tensor decomposition is one of the problems I think is closest to neural network from a technical point of view, because for all of the problems except tensor decomposition that we can understand, there are some rotational invariance in it. And for tensor decomposition and neural network, they share the property that there's no rotational invariance, but there is a permutation invariance. By permutation invariance, I just mean that, for example, if you take your neural network and you permute the nodes in one of the hidden layers, and the network remains exactly the same in terms of the input-output relationship. And this is true for tensor decomposition. However, you cannot rotate some weight matrix and rotate it back in the next level if you have nonlinearity. Okay, so this is just a general overview, and I'm going to talk about matrix completion and linear ResNet in this talk. So I often got asked the question whether there's any unified theory behind all of this non-convex optimization. So I guess the short answer is, unfortunately, or maybe fortunately, for the in terms of the research, we don't have anything yet. However, they are kind of candidates. So the candidates is that there is a general kind of conjecture that maybe this non-convex optimizations in practice is easy because the objective function has very nice geometric properties. So for example, one property that we know suffices is that all local minima are global minima. So if this is true for your objective function, then it can be optimized in polynomial time, because gradient descent or some other local search algorithm can converge to local minima in polynomial time under some very mild regularity conditions. So this is the kind of the common property of an analysis in these problems: SVD, SDP, linear neural network, matrix completion, so on and so forth. So this is a plot of a function with this property in 2 dimensions. So you see that they are 4 global minima here with error 0, but actually they are saddle points like here, and also there's a saddle point around the peak. So but there are no any other bad local minima. Okay, so another property, a stronger property, strictly stronger property, is that all critical points are global minima. So, by local minima, I mean that the gradient is 0 and the Hessian is positive semi-definite, and the critical points just means that the gradient is 0. So if all critical points are global minima, then we also know that you can converge to the critical points in polynomial time, and actually we have a fast algorithm to do that. And this is the geometric property behind these problems: Gaussian generalized linear model, linear recurrent network, linear ResNet. So this is another example of functions with this property. And you can see that the only place with gradient 0 is this kind of line, and this line consists of all of those global minima.
Can you explain what you mean by ResNet?
Yeah, I'm going to define it. Yeah.
Okay. Because this talk is also hosted on ResNet.
Oh, yes.
So people get confused.
This is a residual network.
Is it
If
the
that's
one that proposed 1 year ago in computer vision? So okay,
yes,
I know.
yeah, by the He et al. In my
I was just
on my
wondering
side.
if there's another definition.
No, exactly.
And also, like any of these problems NP complete?
In worst case, sure. If how do you say a problem is NP complete? You write down some objective function and you say, okay, optimizing this function is NP complete. Yes, I think maybe all of them. Yeah, it should. No, not for the linear ResNet. No, not for the linear case. Let's see. Yeah, maybe not this linear neural and linear ResNet, because these are not real machine learning problems. These are more or less test problem for understanding optimization landscape. I'll cover that in a moment. Any other questions? Okay, so however, so these properties are good, and we know that under if the function have this property, then we can optimize it efficiently. However, the difficulty is often not about the optimizer. It's really about how do you verify the object function has these geometric properties. So just to this is not the same as this doesn't happen in complex world, but in the convex world, because usually if you want to verify your function is convex, you just say, okay, maybe your function is a sum of convex functions, and each of term is convex, then the sum is convex. So, however, these kind of properties are not even preserved under addition in general. And sometimes the reversing happens. For example, you have a sum of things, and each of them doesn't have this property, and you take the sum, and you start to have these kind of properties. So, so we don't have very good, ways to verify these geometric properties. That's kind of like a technical goal of this line of research is to develop more mathematical tools for characterizing the landscape of these non-convex functions. All right, so this is the general big picture, and let me talk about matrix completion next. So the definition of matrix completion is simple. So we have a low-rank matrix M. We only observe a random subset omega of the entries of M, and our goal is to recover all of the entries of M. So the typical application of this problem is recommender system. So the typical scenario is that you have this user item preference matrix, and each entry is the the rating of user I to item j, and you only observe a small fraction of this matrix because not every user rates every item online. And the goal is to recover all of the entries so that you can recommend the items to the users. Okay, so concretely we are going to focus in the subcase of matrix completion in this talk. So the symmetric version, where we assume M is of rank R, and it's symmetric and positive semi-definite. So this translates to that M is of the form that M is equals to Z times Z transpose. Here Z is a tall matrix of dimension D times R. D is the ambient dimension, R is the inner rank. So, and we assume that each entry is selected into omega, the set of observations, with probability P independently.
Like Z and Y. Here you assume the same one?
Yeah, so this is that's why this matrix is a special case.
Okay.
Yes. So so we are going to do non-convex maximization, and our variable is this low rank factor x, which is of the same dimension as z, and ideally we want x to be z. And the loss function that we analyze is the following, right? So basically it's the sum of the errors on every observed entry. So here XX transpose is the matrix that we predict, and XX transpose sub ij is the ij's entry, and we take the difference between the prediction that we have and the real value, and we take the sum of squares of the error over the observed entries. So it turns out that it's useful to define this notation up front, just to simplify some of the notation. So let's define P omega of A as the restriction of A to the subset omega. By this, I just mean that, we have this matrix A and the blue entries are in omega, and P omega of A is just, you zero out all of the entries outside the omega, and you keep all of the blue entries inside omega. So using this notation, we can rewrite a little bit succinctly, this objective function as P omega of M minus P omega of XS transpose for binom square. So for binom is just the sum of squares of the matrix. So we can have this. Okay, so this is our objective function that we're going to analyze, and here's our main theorem. So under the usual assumptions, all local minima of this function f are global minima, and they all recover the underlying matrix M. So just to define the terminology here, so local minima means points with vanishing gradient and a positive semi-definite Hessian. This in particular implies that stochastic gradient descent finds a global minimum with arbitrary initialization in polynomial time, because stochastic gradient descent can find the local minimum, and here all local minima are global minimum, therefore stochastic gradient descent can also find global minimum. Okay, so just to clarify what do I mean by usual assumptions, I mean M is incoherent while conditioned, and the sample complexity, right, the expected number of observations that we need should be larger than d times r to the 6. So basically, for each row you have r to the 6 observations. The optimal sample complexity is d times r, and so we lose polynomial factor on r compared to the optimal sample complexity. But we didn't really try very hard, and the main priority is to get the factor d correctly. So I won't define incoherence and well condition in this talk, because they won't appear another time in this talk. So I'm trying to sweep it under the rug.
Seems to be a deterministic statement.
Oh yeah. So I should say with high probability over the choice of omega, this is true. Yeah.
And how sensitive is this to noise?
So we can also prove a noisy noise version. So if you don't observe the exact entries of M, but you observe M plus some noise, it's also fine. So but you don't get exact. So here you get exact recovery of M, and if you have noise, you don't get that. Any other questions? So I also cheated a little bit about the objective function that we are finally going to analyze. So in fact, we are going to add a regularizer that enforces incoherence, although I haven't defined incoherence for you. But this is not important for this talk, for the purpose of this talk. So and there are other properties that probably help to build up the intuition. So f is not convex, first of all. And also there exist critical points that are not global minima. And also another property that is useful is that all global minima have the form that x is equals to z times r. Recall that z is the ground truth factor. And so basically if you rotate the ground truth by any orthogonal matrix, it will remain a global minima. Okay, so
how tight is this d times r 6 power? The r to the 6th power.
Mm-hmm. How
tight?
Yeah. So the optimal complexity that we know, if you use convex relaxation, this is d times r, without the power 6. And we to be honest, we didn't try very hard to reduce this power. So I think if you just use our thing with a little bit tightened analysis, maybe you can reduce it to r to the 4 or something like that. But if you want to do it really well, I guess we need a little bit better analysis. Yeah. But I guess the priority is to make the dependency on D correct. I think that's the first priority. Yeah.
For the convex relaxation is for the SDPs, right?
Mm-hmm.
Those there you just showed that the solution will be the. There's no.
Okay.
This is a unique model.
Yeah. Okay, so this is the main result, and just to compare with previous works, so Candice, React, and others use the nuclear norm minimization or convex relaxation to solve this problem, and this line of research, have the strongest theoretical guarantees, and they can achieve almost optimal sample complexity. And the only drawback is that the runtime is a bit slow, because you have to do the semi-definite programming. Maybe you can speed it up, but still you have to at least store your variables, like d-square variables. And there's also a lot of papers about non-convex optimization for matrix completion, but they all require good initialization. And in fact, the initialization, so Sun and Luo 15 show that the initialization required by all of this paper is sufficient good so that around the neighborhood that contains the initialization, actually the function is convex. So all of this paper actually are analyzing, non-convex method for convex functions in some sense. So, and we don't require any initialization, any special initialization. Okay. So I have defined the problem and state the results. So next, let's try to move on to the kind of the principle that is underlying our analysis. So we call it geometric properties preserved by random sampling. Okay. So what I mean by this is that this is our object function that we want to analyze, and we compare this with the full observation case, where you observe all of the entry, and if you observe all of the entry, there's no problem to be solved because we just want to recover the matrix, but still we can analyze the the landscape of the optimization landscape of this function, right? We can say we just want to look for the factor and we want to minimize this objective function. So as you can see, this partial observation case is just a random sampling of the full observation case, because recall this is the sum of the errors on the observed entry, and this is the sum of the errors on everything. Okay, and the kind of the point that here is we want to argue that these two functions are actually similar to each other in terms of many geometrical properties. And the first one is that the full observation case is easy to see that any global minimum X satisfies that XX transpose is M, right? That's with zero error. And we can show that for the partial observation case, this is still the case. The global minimum recovers the matrix M. And this is kind of known and is sufficient for the statistical purpose in the sense that if you just care about some algorithm, you can do some numeric search and solve this non-convex optimization by a brute force way, and you solve the problem. However, to have computational efficiency, we need the stronger properties to be preserved. So this is the property that we're going to prove, that all local minima are global minima, and it's kind of folklore that this problem has this property, and the thing that we want to establish is that the partial observation case also has the same property. So this will imply computational efficiency, and this is the main object, the subject of the talk, the rest of the talk. Okay, so just before getting to details about analysis, let's have several plots to give you some intuition. So it's hard to plot a d-dimensional function. Just to visualize it, it's hard to visualize a d-dimensional function. And what I'm going to do is that I'm going to restrict this objective function to a two-dimensional subspace. I'll choose some special two-dimensional subspaces and just visualize the objective function. So this is a rank 1 case, and we have a random choice of v, And we see that this is the plot for the full opposition case, and this is the plot for the partial opposition case, and they look indeed quite similar. And also you can see that there is a saddle point here, and probably there are two local minima in the symmetric position. Okay, and you can also see that here the error. So this is from 0.7 to 1.1, so the error is not 0. This is just because in a random subspace you are not going to have the real global minimizer, so that's why you won't really see 0 error in this subspace. Just a small warning here is that these plots are only meant to be illustrative because in some sense there's the only way to certify all of this geometrical property is by rigorous proof, because you cannot really use any visualization to certify anything about the dimension. At least it's not trivial to do that. So this is also why I kind of love this line of research, because you really need theory to prove things about it. Okay, so we can also choose a different subspace V. So here we choose V to contain the two global minima. So just recall that in the rank 1 case, there are only two global minima. Right? One is the matrix and the vector matrix Z, and the other is minus Z. And we choose a subspace that contains these two global minima. And now we see that we have two global minima even in subspace with error 0, and these two functions indeed look pretty similar. And we can also do this for rank 2 case, which is kind of conceptually different, because for the rank 2 case, any global minimizer X has the form X is equal to Z times R, and R is an arbitrary, unitary matrix. So there are infinite number of global minima, and they all form, they are connected, and technically they are on a Grassmannian manifold. So, and what we do here for the plot, we choose a subspace V that can contain 4 global minima. We cannot choose, so they are in a symmetric position, and we plot the function restrict to this subspace, and we see that we have 4 global minima, and they are, critical points, 5 critical points in this plot. Okay, so these are just some plots to build up some intuition. Okay, so the next thing we are going to do is the analysis. So our technique, actually I hesitate between which line I should show here. So Occam's proof carry over, but that's just a fancy way to say simple proofs generalize better. So I guess let me explain this. So let me just make the point that generalization is difficult in theorem proving. So let's say this is myself here in trying to learn how to prove theorems, and learning to prove theorem is hard, right? Because let's say suppose I'm very talented, I learn how to prove the 10 greatest theorems in history. Of course, I don't know how to prove any of them probably, and I learn all of these theorems, and now let's test whether I learn anything. So let's test Fermat theorem. Right? So of course I don't know how to prove it. Even though in the tuning example there's a Fermat-Little theorem, which sounds sufficiently close. So I just want to make the point that generalization in human learning is a problem. And this is indeed the kind of the difficulty that we face here, because we are trying to generalize from one example, right? We have the full opposition case, which we almost understand, and we want to generalize it to partial opposition case. And we only have one example. Okay, so and before going to in some sense kind of the difficulty is that the search space is too large. There's so many proof techniques, and you don't know it's like the V's dimension of the possible proofs is too large. And let's just show before going to more details, let's just show a proof technique for the full opposition case which doesn't generalize well to the partial opposition case. So, and just for simplicity, in the rest of talk, let's focus on the rank 1 case, where we assume M is equals to ZZ transpose. And so now I'm using a little letter to indicate that Z is a vector. So Z is a D times 1-dimensional vector. I also use the notation little x instead of capital X, for the variable. And my objective function in the full observation case is this m minus x as transpose for binom square, and the partial observation case is f of x is equals to p omega of m minus p omega of x as transpose for binom square.
The point of doing that would be to simplify the derivatives.
Okay. For rank 1? Yeah. There are other benefits. Yeah. Okay. Yeah. So like for the rank R case, the choice, this proof will be a little bit more delicate, but not as efficient. I mean, essentially different, but yeah. Anyway, so right. So let's have so in the rank 1 case, we want to prove that the only local minima of G are plus minus Z, and so let's have so this proof for this claim is actually pretty simple, right? It fits in this small space. But this proof won't generalize, just to mention that. So let's take the gradient of G. So it is equals to mx minus square norm, the norm x squared times x. So a local minima satisfies two things, right? The gradient is 0 and the Hessian is positive semi-definite. So gradient is 0, we solve this system of equations, right? Note that this is a scalar, so mx is equals to some scalar times x. That means that x is an eigenvector. So all critical points should be eigenvectors of m, and we can just plug in each of the eigenvectors into the Hessian and see which one has positive semi-definite Hessian. I skipped some of the calculation, but it can be easily seen that the Hessian is positive semi-definite implies that x has to be the top eigenvector. And the top eigenvector of m is z, or minus z. So, and we are done. However, I'm going to argue that this proof is very difficult to generalize. So, for the partial observation case, we want to prove that all local minima of f are plus minus z. So, let's try to argue why this is hard to generalize. So we can try to imitate the proof on the left-hand side. Let's say we compute the gradient of f, right? It is of this form, and now we get into some trouble, right? How do you solve the system equation that gradient of x is 0? So before we can do it, because it's kind of a tautology, right? That's the definition of eigenvector, is the solution of this system equation, and now you lose all of those nice linear algebraic structure. Let's say even you can, in some sense, solve this system equation. What are you going to do next, right? You have to, plug in your solution into the Hessian. If you don't get, if you only get some approximate solution for this, then it's very hard to control what's going on for the Hessian. So I'm not saying it's impossible, but it definitely sounds very complicated, and you need probably better tools to handle this. Okay, so the kind of the lessons that we learned from the previous slides is that spectral information, linear algebraic tools could be brittle to randomness, especially if you use it twice, once for the gradient and once for the Hessian. All right, so the high-level plan that we want to proceed is that we want to find an alternative proof for the full observation case, which is generalizable. And what kind of proof is more likely to generalize to partial observation case? So I guess the question is, what kind of proof techniques are robust to random sampling? I'm going to argue that this is a type of proofs that will be able to generalize. So the proofs that consist of only statements that are linear in indicator of omega. By that I just mean that statement of this kind of form, right? A sum of wij over ij in the subset omega. So this is linear in the indicator because you can rewrite it as this. And the reason why this kind of statement is generalizable is that just by a law of large number, you have a sampling of a sum, and the sampling version will reflect the original sum pretty well up to some constant factor, which is the sampling probability. Okay, so let's call this Occam's proofs. Just for this talk, if you are not familiar with the story of Occam razors, this just means simple proofs in some sense.
In some sense, it's like making using an abstraction algorithm in mathematics to create a more general statement.
Yeah.
High abstraction rather than full kinds of proof.
another way to say it.
Sure. Yeah. Yeah. I guess I would like. Yeah. So the reason why I thought, I said this is simple because compared to linear algebraic things, which actually use a lot of things behind it. How do you prove that the eigenvector even exists? Right. You need to, use the fundamental theorem of algebra to show that the determinant has roots. Right. But this kind of things doesn't require anything behind it. Only concentration, law of large number. Okay, so I guess the bottom line is that Occam's proof are robust to random sampling and thus generalize better. So let's have some examples of Occam's proofs. So let's say recall that P is the probability that each entry is selected into omega. The key fact that we are using here is the following. So if you consider the inner product P omega of A and P omega of B, right? This is the matrix inner product. You just view the matrix as vector and take the inner product. And this is equals to A times P omega of B because they both equals to just the sum of Aij, a sum of Aij, Bij over Ij in omega. And again, by law of large number, the sampled version should be close to, up to scaling factor, close to the inner product between A and B. Okay, and this key factor has several corollaries. So if you take A is equals to B, we have that P omega of A Fourier norm square is close to P times the Fourier norm square of A. And recall that our object function actually is of this form, right? Our object function is P omega of M minus XX transpose Fourier norm square. So this means that the object function itself is linear in the indicator of omega. And because gradient and is a linear operator in the functional space, actually the gradient has in all linear indicator of omega. So basically, in some sense, as long as you don't solve system equations, you are fine. And also we need a little bit stronger things with the statement with quantifiers. So we need this kind of statement with high probability of the choice of omega for every x in d dimension. This is just another example of this key fact, right? You place A by XS transpose and B by M, and but the point here is that we need for every x this kind of a relationship is this approximation is close. It's good. So just to note that not all statements like this are true, but this talk will ignore such issues. So to fix this, it requires a little bit technical things, but those are not quite the point of this talk, I guess. So for this talk, we just pretend that all of this kind of statement with quantifiers are fine.
Can you just spend 1 second saying
Sure.
what you mean by like this? I mean, what is it about the ones that you do like? That
So I just mean that basically, I guess I'm saying that any statement like this, if you replace A and B by something depending on M, X, whatever, will be true, up to some additive error.
when you say not all statements like this are true.
Yes. So yes.
So is it not all x's? I mean, what?
For all
Then-
x.
When you say not all, what?
Oh, not
what,
all.
What all quantifier are you
No,
saying is
not
not
all. Let's say this whole thing is a statement,
true? Uh-huh.
and not all statements like this whole statement and this whole thing is true.
What are you quantifying over in this all? The m or omega?
This
or-
all.
Yeah. What is this all referring?
This all is referring to all types of all similar statements like this.
What changes from statement to statement?
So for different statements, you have different concentration properties.
But can you just give us a clue what you're talking about here?
Okay, sure.
Just one
Maybe let me write something that is not true on the board.
Yeah.
Okay.
Sorry, I think I cut that line out just to save time. So, for example, this statement will not be true with high probability over omega for every x in dimension d, x transpose, let's see, p omega of x transpose is close to p times x transpose x. So this is a similar statement like this, right? It's another corollary of this fact. but actually it's not true with this strong quantifier.
So the all refers to the matrix M.
The all refers to this type of, this is a vague thing. But I guess we don't have to worry too much about it. Anyway, we're not going to talk about it.
Like the interesting thing that basically, there you have a. So this is very similar to our first step, but there's linear matrix A and B. But now, if you even put the matrix A B to be the after product of vector, then it will no longer true. That's the second order effect out there, right?
Yeah, yeah. And, in the final proof, we are going to use a lot of different statements like this, like not just the X as transpose, maybe X Z transpose, and this is something else. Sometimes you have to plug in something crazy, but let's pretend all of them are true for this talk. So those kind of the technical things.
So is this statement looks like some sort of sparsification?
This is just the spectral norm of this P omega minus P times M. It's small, so but sometimes it's not that simple.
Technically, you're just doing a union bound over an epsilon
Yes.
net.
So the way to
And
prove
then
this kind
you
of
use
concentration is by union bound.
And then you want to use the Lipschitz-ness of what you're union bounding over, like the function that you're concentrating.
Yes.
It's not true because of this one is Lipschitz, so that works.
Not exactly, but
Okay.
yeah. But Lipschitz-ness is not a problem because the dependency on the Lipschitz-ness is logarithmic. So if you are willing to lose log, but that's those are we can do that. I mean, we can discuss it offline. Yeah. Okay. So I think probably what's a little bit more important is how this kind of statement can help and how do we use them. So let's prove this simple lemma using this kind of outcomes proof. It says that the gradient 0 implies that x inner product with z square is equals to the false power of x. This lemma itself doesn't have any special meaning. We don't have to care too much about it. Probably the important thing is what's the flavor of the proof that we want to have. Oh, sorry.
What is
Z is the ground truth. Like M is ZZ transpose. Oh, actually I have it. Sorry. Okay, so this is an outcomes proof that will generalize. So we first write down the gradient, right? It's equal to ZZ transpose minus XI transpose times X. And the gradient 0 implies that, X inner product with gradient is 0. So, and this is, we replace the gradient by this form, and we get X times ZZ transpose minus XI transpose times X is 0. And by just algebraic manipulation, we get the desired statement. So this is very simple. And now let's see why this can be generalized, right? So we claim that we're going to prove the same thing for the partial case with just an approximate equality. So here's the generalization. We first compute the gradient of f, which is of this form. And then we imitate the proof on the left-hand side. We take x inner product with gradient of fx. This is, again, 0. And then we replace the gradient of fx by this special form. And now here it comes the point. So if you look at this guy, this is just a random sampling of this guy. And by concentration inequality, we can show that for every x, these two quantities on the left and the quantities on the right are close to each other. And because they are close to each other, you're going to get the same conclusion out of them. So with a little bit, approximation. So basically, kind of to summarize, because you have a proof that is linear indicator of omega, it will generalize to the observation case with some approximation. Okay, so this is just a small lemma that shows how do we use the information the gradient 0 without solving the system equations.
Looks like you're using exactly what you said was not true.
I guess so. So the way to fix, okay, I guess I shouldn't delete those technical things. The way to fix it is that you can say for every x that is incoherent, this is true. And for those x that is not incoherent, you add some regularizer to change the geometry so that it's better.
And what is the regularizer? Can you write the formula?
Okay, I really shouldn't delete those things. So the regularizer, I think I have a slide. Okay, maybe let's write it here. So the regularizer is that the R of X is sum of, let's say, ReLU, something like this, square. Yeah. So if xi is larger than tau, you're going to penalize it. And if xi is smaller than tau, you're not going to do anything. ReLU is max of this guy and 0. So you don't change anything inside the incoherent ball, and you change the geometry a little bit outside the incoherent ball to make it better.
But it also sort of depends how many x you need to quantify anyway, right? I mean,
yeah.
I mean the criticism that you're using, what you said you couldn't is, I mean, if there's only one or a few x's around the gradient to 0, it's much smaller.
Yes, but we are going to show that for all x that is incoherent. For all, really for all. Yeah. So, okay, sure. So, okay. So now let's see how do we use the Hessian information in a way that is linear in the indicator of omega. So this lemma says that the Hessian is positive sum definite implies the norm of x is larger than a third. And on the right-hand side, we're going to prove with a small, slightly smaller constant. So recall that Hessian is linear in indicator of omega, and that implies that the quadratic form over the Hessian is also linear in the indicator of omega. And what we are going to do is that the Hessian is positive sum definite. We are going to choose a special vector here. We choose z here, z the ground truth, and this implies that this quadratic form is non-negative. And this is a linear statement, let's say linear in omega. So okay, for the full opposite case, what we can do is that we can have we just do some simple elementary calculation, and this implies that norm of x is larger than a third times norm of z. And the norm of z is assumed to be 1, and so we get 1/3. So on the right-hand side, we get the Hessian of f is positive sum definite. We choose the same vector, right? To hit the quadratic form, we get z times the gradient, the Hessian times z is larger than 0. And because this is a statement that is linear in omega, we have concentration inequality here, just to show that these two are similar to each other. And because they are similar, you can use exactly the same elementary calculation and get the same outcome, just with a little bit approximate inequality. So that's why we get a slightly smaller constant. Okay, so just to get a little bit intuition, why we want to choose z in this quadratic form? The reason is that in the full observation case, this is the Hessian, right? X transpose times some function scalar times identity minus z transpose. So basically, z is kind of approximately the most informative direction that you want to care about. And this Hessian, that's why we choose z, evaluate z. Okay, but presumably you can also do something else, So, okay, so these two lemma, together actually already achieves a little bit, right? So if you use these two lemma together, what you're going to have is that we plug in the lower bound of the norm of x here. We get that x is a local minima implies that x dot z square is larger than 1/9. And in high-dimensional space, if you have two vectors that are constant correlated, that's already in some sense a bigger achievement, because two random vector has correlation 1/square root d. So and on the right-hand side, we can prove it with a slightly small constant. And of course, there are many other steps to complete this proof, but they are kind of similar, and kind of the rationale is the same. You want to figure out basically a long and simple proof for the left-hand side, and they will generalize to the right-hand side. So I'll skip those steps for the talk. Okay, just in high-level summary. So we only need a simple proof for the full observation case, and that suffices because it will generalize to the partial observation case. And this is can be done also for the rank R case, and potentially this also can also be done for the asymmetric case. And we believe that we can use the same technique for many other problems with partial or noisy observation. So I guess the devil in the detail is that sometimes concentration is not good enough for non-incoherent x. That's related to what we discussed here. And the fix is to add some regularizer to modify the geometry at those non-incoherent points. So, but I decided to hide these details because these are just for theory in some sense. Like in practice, I run experiment. You don't need all of them, and we don't really know. I mean, it's kind of clear why, because in practice, those kind of worst case things may not happen, and so in practice you don't need a regularizer at all. Okay, I guess I'm running pretty late. Probably I can even skip the second part. Okay, so
Which part do you want to skip?
the linear ResNet one.
You should.
Okay, it depends on. Okay, sure. So so this is the conclusions, right? So we proved that matrix completion has no spurious local minima, and the phenomenon is the geometric property is preserved by random sampling, and the kind of the proof techniques is outcomes proofs carry over. Okay, some open questions. The first one is whether we can get better better sample complexity analysis, and also faster runtime. So, the question is runtime also a property that is preserved by random sampling? I ran some experiment, and just to verify this conjecture, it turns out that this is indeed true. Right? These are the runtimes of several choices of different choices with the p, and it seems that they all converge pretty fast. So I guess they are this. Oh, this is because the p is too small, so that you don't have enough samples. Yeah, I just want to keep it there just to show that p has to be reasonably large. Actually, there are other points in this. Okay, maybe I'll skip other points about this slide. But this is a conjecture that we have. We didn't really think too much about it, but it sounds something that can be proved. Okay, so and there are some other open questions about nonlinear case. For example, one-bit matrix completion, nonlinear PCA, or weighted SVD, which has applications in word embeddings. Okay, but these are the open questions. So guys, any questions before I switch gears to a new paper? Okay, so
10 minutes for the second part.
Okay, sure. Okay. So I'm going to talk about another related paper. The title is Identity Matters in Deep Learning. So this is with Maurice Hart. The kind of the punchline here is that reparametrization with some identity connections makes the optimization easier. Okay, so let me introduce the neural network, right? The vanilla one, just for the sake of comparison, right? So in neural network, you have this, many layers, and each layer has some weight matrix. And mathematically, this just means that each of the layer hi depends on the previous layer by a matrix multiplication and some ReLU, some nonlinear activation. So this is the vanilla neural network. And in this residual network proposed by He et al., so they use this reparametrization. They add this connection, this identity connection from layer 0 to layer 2 and layer 2 to layer 4, so on and so forth. So by this, I just mean that the second layer is depends on the first layer, right? And you add identity times the zeroth layer to the second layer. So mathematically, this just means that hi in the odd case, right, is just the same as before, but in an even case, hi is a linear transformation and ReLU, like a ReLU of linear transformation of hi minus 1 plus identity times hi minus 2. Okay, so this residual network achieves state-of-art results for CFAR and ImageNet. It sounds like it's a kind of on many tasks is a better model. So the kind of the original rationale in some sense behind it is that to have this identity mapping here, so to have this identity connection here makes the identity mapping easily implemented. So for example, by this I just mean that if you want to implement identity mapping, the only thing you need to do is you need to take all of these matrix AIs to be 0, and then this jump connection carries over, take care of it. So however, just for comparison, on the left-hand side, even if you take AI to be identity, you are not going to implement identity mapping because they are nonlinear activation functions in between them. Okay, so and actually we can indeed prove that we can use n log n parameters to fit any labels of n examples. This just says that the expressive power of this network is very high, is very good. So if you have n examples and with any labels, you can use n log n parameters to fit to it.
It's not
So
the case for the vanilla neural nets.
It is also the case for the vanilla neural network, but it requires a very kind of strange one. You need a very very wide layer and with some parameter sharing. So but for this the proof is relatively simpler. But anyway, these are all simple proofs, kind of trivial. Okay. Also, this is not the main point. The main point is how do we analyze the optimization landscape? The kind of point is that we want to make is that this reparameterization not only matters for expressiveness, but also matters for optimization. However, the main difficulty here is to handle all these nonlinearities in neural network, and we don't really know how to do it yet. And it sounds like it's beyond the scope of the current technique. We really need more techniques to understand nonlinearity. However, what we can do is that we can analyze a simplified model just for first-cut understanding of the optimization. Understand why reparameterization matters. So fortunately, this reparameterization, the phenomenon of reparameterization already occurs for the linear case. When you have a bunch of linear matrix layers without the nonlinearity, you can still see the power of reparameterization. And this is what we are going to do. So we have, so now we have no nonlinearities. So every layer is just a matrix multiplication. And also we make this, for simplicity, we make this connection instead of a jump connection from 0 to 2, we just make it from 0 to 1, 1 to 2. It doesn't make any difference. So basically, mathematically, the ith layer is just a linear transformation of the I-1 layer plus the identity times the I-1 layer. And the final output is just the product of bunch of matrices times x. Okay. So, and the loss function we are going to study is the L2 loss, and here the true label y is a linear transformation of x. So basically, we are in a very kind of dumb scenario where we want to learn a linear classifier, linear transformation using a deep linear network with reparameterization. But just the goal here is to kind of understand the optimization landscape. So that's still the optimization landscape is still non-trivial in this case. And so the population risk that we're going to analyze is the expected loss over the samples, which is just this. This is y hat and this is y. Okay, so let's start with a simple lemma.
So what's the expectation? Where's the randomness here?
The randomness is over the samples. The input. X is the input.
Oh, I see.
Okay, so let's start with a simple lemma. So there exists a global minimum of f such that the norm of these matrices are smaller than 1 over L. So this basically says that if you make the the number of layers more and more, you only need smaller and smaller matrices. This is kind of intuitive because you have a product of bunch of matrices. So if you have more products and more items, you can make each of them relatively smaller. Okay, so and this has some log factors, which is not important, I guess. So, and the theorem that we're going to prove is that if this configuration A1 up to AL is a critical point with vanishing gradient, and L satisfies that the max of the spectral norm of AI is less than half, then this is also a global minimum. So, in other words, in words, this residual neural network has no bad critical points. All critical points are global minimum. And just for comparison, if you don't have this identity connection, it can be shown that all local minima are global minimum, but they are bad critical points. So we have a stronger and more desirable properties by doing this reparametrization. Okay, I guess I can skip the proof sketch and just jump to the wrap up. So again, the punchline is that the parametrization with the identity connection makes optimization and representation easier. I guess the open question is, how do we analyze, the optimization estimate of the nonlinear case? I think we are getting close. So kind of one hope, is something just to connect to the matrix completion thing. So recall that linear residual net is kind of like a test case for us to understand the nonlinear thing. This is kind of the same situation as we had for the matrix case, right? We started with a simple case and we went to generalize to the complicated case. So it sounds like we again need some Occam's proofs for the linear residual net, which doesn't use all of these nonlinear which doesn't use all of these linear algebraic tools. So if you have a different proof for the linear residual network, maybe it can generalize to nonlinear case. That's just a hope, okay? So, and another thing is that maybe algebraic geometry tools are possibly be useful if you're only dealing with critical points. In some sense, the problem with dealing with local minima is that you have this positive semi-definite constraint, and it sounds like it's beyond scope of algebraic geometry because you have semi-definite. This is kind of like real algebraic geometry, right? We have inequalities, and however, if you believe that we can only deal with critical points, then the algebraic geometry thing might be useful because you don't need real algebraic geometry. That's a big relief, I guess. But that's just some hope. Okay, I guess I'll stop here. Thanks.
Questions, comments?
I'm actually curious about the slide you skipped. I mean, how did you go from the statement that like all the critical points? Can you go back to 2 slides and?
Oh, the proof sketch?
Yes. So.
It's very simple. So let's do it. So it's very simple. So we calculate the gradient. Because believe me, you can calculate gradient. Gradient is like this. The gradient is a product of a bunch of things, right? Some of them are I plus AJ transpose. And there's an E here, there's a sigma here. E is the error, basically. So how well your network fits the linear transformation. And sigma is the covariance of the data. And let's assume that sigma is well conditioned. The least singular value of sigma is strictly larger than 0. And then, also note that because each of the AI has spectral norm less than half, then the minimum singular vector of AI I plus AJ transpose is larger than 0, actually larger than half, by triangle inequality. So that means that this is a bunch of things, a product of a bunch of things, except E here, all of the other things are well conditioned, like have singular vector, least singular value larger than 0. And if the gradient is 0, that implies that E is 0. And E is 0 means that it's global optimal. So that's also, this is strictly simpler than a case when you don't have this identity connection. Like it requires a more subtle analysis, like complex analysis.
So in real problems, real deep learning problem or this resonance or something, is there evidence for or against the statement that really something as strong as this is true, that all global minima are local minima or something like that? Or is the suspicion that it's more complicated, but that's approximately true? Or maybe there's just no evidence.
I think there's no evidence against them. So first, let's take the weakest one. So the all local minima, global minima. I think at least there's no really evidence against it. And actually, in fact, there is evidence that supports it because.
I don't believe that. It could be that there is that the global minima is 0, and probably you can show local minima which are above 0.
But I think
but also what exactly you mean by neural network? Is it for one.
But even a few layers.
So the empirical evidence.
Empirical evidence.
So in this case, I guess in this case for the linear ResNet, the empirical case is not really local minimum even. I think people was more excited about how fast the trend. Right? That's the first order effect. And the local minimum with or without it, that is my reading.
Sorry.
So with local minimum now, get different result. There's not, people say all comparable, but people are excited about how much faster trending. That's the main thing. You can cover things much faster. Yes.
And there's another issue that, often people are training these networks for random initialization that the networks don't converge. So clearly.
Don't converge?
No, convergence, at least with the very large, computer vision classification tasks, I definitely know that there are cases where people have trained the networks from some starting points. It's not giving them good results.
It's not clear what happens. Right? So first of all, for most of the successful case, of course you can design some, weird case so that it's not true. But in all of those successful cases, at least for now in computer vision, the training error is always 0. So you can even have, at least it converges to global minimum. 0 is the minimum that you can achieve. So this is the evidence that supports this thing. And also regarding the initialization, sometimes you don't really know what happens. So for example, if you initialize the weights to be too large, then it's possible that you just need a smaller learning rate, or it's a very weird place which you can rule out by other means. When I'm saying that all local minima global minima, this mean we should take this. It's not a. It's not a complete mathematical. For example, you can say, okay, in this region, all local minima global minima. That's also fine, right? So, but I believe that that's at least partially the reason for why all of this can be trained. Also, for example, another example is that if you initialize all of weights with negative numbers, then you are going to have a critical point, right? The gradient will be 0 because the ReLU zero out everything. So that's another bad example. However, those things shouldn't count, right? When you talk about these kind of things.
All right, let's thank you again.
There's a